तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Until now we have been seeing circuits which are called combinational circuits. I think I mentioned this once to you earlier. A combinational circuit is defined as a circuit in which the output changes with the input. That means the outputs are influenced only by the present inputs. On the other hand, we have another class of circuits called sequential circuits. That is what we will start today. As the name implies, sequential circuits have some sequencing in it. What it means is the output, of course, depends on the input. In no circuit can the output be not dependent on the input. There are some circuits like that, special circuits, but we will not talk about them now. But generally, a circuit will like the output to be dependent on the input, but not only on the inputs, but also on the past behavior of the circuit. As an example, a counter. I give a count, let us say count pulse, count 1. That means you should count 1 from what it is right now. The count now is 7, next count should be 8. If I give a count pulse again, from 8 you should go to 9. This is what I mean by sequential circuit. By the behavior of the circuit of counting depends on the input count pulse. Input pulse count has to come for it to count, but it should count from where it left. Right? This is what we mean by the past behavior of the circuit or past outputs. The present input as well as the previous output or previous outputs. But we don't have to say outputs because previous output would have been the one before that. So it is a history that is built in. So the present input along with the past output or outputs determine the present output. Such a circuit is called a sequential circuit, and it is very important to have such circuits. Why is it important to have these circuits? Why? Because we need to have a pattern of behavior. In a traffic light controller you are trying to design, we have a timer which times the duration for which a particular light is on. You should know what light it should go to. That depends on the previous light. If I had 2 lights, green and red and green, 2 roads, let us call this road 1 and road 2. In road 1 it has been red now, go to green, based on whether it has been red for a while. The same road, next time, after the next timing, it should not change from green to red on the same road. So the green for one road should be for a certain duration, and after that the next green should be for the second road. Only then the traffic from both roads can move. If you don't have that the past output, that the previously we changed the road 1 from green to red, and now the second road has now changed, then you don't want to go to the same first road and then change it back to green. The second road keeps red all the time. You don't want that. So you want some sort of a previous behavior. What is the previous pattern? I already told you the example of the counter. I need to know the count, the present count. That can be given only by the past count value, and then the present value whether the count has to be done or not. So it's very important in any circuit, there is any circuit of meaningful circuit, any design, any hardware, any system that you build will have to necessarily contain sequential circuits if you want to have a behavior pattern as per a sequence of events. Elevator control, even rocket launch, a series of things, a sequence of things have to happen, not abruptly. Something should happen. That means some sort of a past history of the output has to be available for the circuit to make a decision, right? How can I say the circuit output has to depend on the present input and the past output? How I have to have a way of remembering the past output. I should make available to the past output to the circuit present at the present time. At the present time, I need to give the past output along with the present inputs. That means I need an element, a storage element, a component which can store the value and give it at the required time. Such an element is a memory. You need to have a memory. The history has to be remembered. You can remember it only with a memory. So a sequential circuit will contain no doubt combination circuit, because once the history is given, it will consider that as one of the inputs. That's all, right? The combination circuit takes the inputs and gives the output. Based on the input, it produces the output. Now the input is one more or many more depending on the previous output. So the previous outputs are also given as inputs. So if this was a combination circuit model, we give inputs and it gives outputs. The sequential circuit model will be inputs, outputs. These outputs will be stored in some storage or memory. We call it memory or storage. What do you store in this? These outputs that are previous outputs. And make these available back under this. So the model of the inputs deciding the output does not change. That is the model of any circuit. The input has to be given, the output will come, and this circuit will still be a combinational circuit within this. So this is combinational, this is sequential. But this block is a combinational block in the sense it combines. What is a combinational block? A combinational block combines the inputs to produce an output. Combines in form using gates and other functional units. So that is still there, but I am going to provide to it some more inputs which are not there in the previous case. These inputs being the past behavior of the circuit. That's all there is to it. It is only an extreme model. It is not that every output has to be considered for every input. No. For every past output has to be considered for considering the present output each time. It may be one output. One of those outputs may determine whatever. This is only a model, a diagram. So this is still a combinational circuit again, which means there is nothing much here for us to do because we already know how to design it. Given an input, you do the truth table, corner map, simplify, get the implementation using whatever type of gates you are asked to do it with, and then we have the outputs. But in between we need to have these elements for storage. This is what is new, the feedback component, the feedback concept, the feedback so that the circuit will remember this behavior. That part is only the new thing here. Once we know how to do that, once we know how to implement this, we can build this combination sequence circuit using this sort of a model. And since we know how to do this, we have already done that part. So this extra thing is all we need to do in order to realize a sequential circuit. And as I mentioned, in any practical circuit there will be a lot of sequential thing, behavior. A computer, supposing I need to do an instruction, multiply. Multiplication is instruction where, of course, we did a little bit of multiplication in our combination circuit. We saw how to do a multiplication. It's a purely combination circuit using AND gates and adders. But I should tell the computer when to do that multiplication. Only when the correct values of A's and B's are available at the right inputs, at the right places, and then I should say do the multiplication. And then the result, the sum or the product, must be available at the right time to the next unit, next fractional unit. So there is a sequencing involved there also. The sequencing is an operation which is required in any system. A system cannot be done arbitrarily, as will become chaotic. You don't want a chaotic system where all circuits are right, but they will function in their own way, independent of each other. All of them will be working, but they will not care about what the input is and what the output, when the output is given, when the output is given, when the input is given, when the output is given. If that is not done, then there is no logic, there is no systematic thing, and then the system, the concept of system fails there. So all we need to do is look at this small piece of hardware, this block. This is how to realize it. So the most common element to store, what do we store in digital circuits? There are only zeros and ones all over. It's all binary. Everywhere is binary. It's a sea of bits. If you can sort of, as if you break open a computer and see inside its brain, you'll see zeros and ones all over the place. Sacks and sacks of zeros and ones. Right? That's all, that is nothing else. So I need to know how to store a 0 or a 1. If I know basically how to store a 0 or 1, I can produce many such storage cells in order to store whatever values I want to store. It can be 1 bit, it can be 2 bits, it can be multi-bit, 4 bit, 8 bits, 16 bits, 32 bits. Whatever number of bits I can do, provided I know how to do one of them. If I know one of them, I know that is what if you remember the introduction, my introduction to digital systems, this course, I said, the beauty of digital is you can duplicate it without any effort. So all I need to do is, that means to find out how to store a single bit, which is a 0 or a 1. If it's a 0, I want it to remain 0 as long as I want it to remain 0. If it's a 1, I want to have it 1 and then have it 1 as long as I want it. If you know how to build that basic component, basic building block, then we know we have conquered the digital system, because that's all is needed here. We already know this, so we can build any digital system. So the basic storage element is called a latch. As the name suggests, the latch, it latches on to the data. It latches on to a 1 or a 0. And it is not a very complicated circuit. It is a very simple circuit. You know this gate. What are these gates? NOR gates. I will call this input, for reason which will be clear a little later on, R, and this input as OO. I am taking R as one of the inputs, and the other input to this NOR gate is the output of this NOR gate. So the feedback is introduced here already. What did I say about this memory? Memory is feeding back, putting the values back into the system. The feedback concept is memory is nothing but a feedback concept. So chewing on what happened earlier, right? That's what a memory does. So that's what is done here. That's all. The feedback is built in, so it should act as a latch to store a bit of a bit, either a 1 or a 0. The second NOR gate has another input called S. As I said, we have specifically named it R and S for some reason. Will become evident pretty soon. The other input of this NOR gate is from the other NOR gate, and then this is called the Q, and this, as you will see, it's called Q bar. That means this and this will be always complementary. You will see that. I got to call it P and Q, and then later on said P is same as whatever, but it's all right. So let us now put what? Let me put S is equal to 1, R is equal to 0. I do not know what the Q was, because earlier these flip-flops, earlier these gates could have been having any outputs. I didn't know that. Irrespective of that, I am now going to introduce an input of S is equal to 1 and R is equal to 0. What is the truth table of NOR gate? Let us write the truth table of NOR gate. A, B, F. Both 0. What is the output? 1. The complement of R, is it not? NOR is a complement of R. Now, as long as one of the inputs is 0, since both inputs are not 0, as long as one of the inputs is 1, the output of that gate has to be 1. So when S is equal to 1, this gate has to have an output of 0. Has to have an output of 0, right? Whatever was the previous output, moment I make S is equal to 1, this output will become 0, and this gate will have input of 0 from here, and since I made R is equal to 0, I am forcing this input to be 0, and this input is 0, so the output is 1. Q is 1 and Q bar. As already we are seeing that Q and Q bar are complementary. Right choice of the variables, Q and Q bar. So when you make S is equal to 1 and R is equal to 0, Q becomes 1 and Q bar becomes 0. Now I am going to make S is equal to 0, R is equal to 0. When S is equal to 0, R is equal to 0, that means this one I am making it 0, this R remains 0, this one I am making 0. Now what will happen now? This is a 1 here, this is 0, 1, 0, so output will be 0 here, this will continue to be 0, and this 0 and this 0 will make this 1. That means this will continue to be 1, this will continue to be 0. Even though I made S is equal to 1 and R is equal to 0 earlier to make it Q is equal to 1 and Q bar is equal to 0, when I remove S and made S is equal to 0, R is equal to 0, already we can see the effect of the previous output somehow. We will see that more clearly in the next stage. The previous decision, previous output of Q is equal to 1 and Q bar is equal to 0 has affected it, because this I deduced this output is 0 because of this 1. I took this one into account. Similarly, this took this 0 into account to determine this one. So q continues to be 1, q bar continues to be 0. Now I am going to make a third combination. I am going to make x is equal to 0, r is equal to 1. When we make s is equal to 0, r is equal to 1, now it can be 0, 1, whatever. S is equal to 0, this is 1. So when you put 0, 1, the s is equal to 0, let us talk with this, r is equal to 1, 1, 0, this has become 0. Even if you assume the other way, it will change again. So we can make r is equal to 1 and this is 0, 1, 0 is going to make it 0, q is going to become 0. Since s is 0, this is 0, this is going to become 1. So q is going to become 0, q bar is going to become 1. But we have taken this first, I could have taken this 1 as this. This is 1, 0, this 1, 0 would have resulted in a 0, and 0, 1 would have resulted in a 0. So this 1 would have, even though I had assumed it to be 1, it would have become 0, and then I have to do one more iteration till it settles down. I have to consider it. Now again I will do this s equals 0, r is equal to 0. This will make it very clear. Input is dependent on the previous output. I mean, the present output is dependent on the previous output. Now I am considering this case when s is equal to 0, r is equal to 1, output of q is 0, q bar is 1. After that, I am one more time making s is equal to 0, r is equal to 0. When I do that, what happens? Now this was 0 now, this is 1. So 0, 0 continues to be 1, and 1, 0 continues to be 0. Now this is a very clear case of, take these two cases. S is 0, r is equal to 0, output is 0, 1. In this case, s is equal to 0, r is equal to 0, output is 1, 0. Why? Because the previous to this, input was 1, 0, which results in output of 1, 0. In this case, the previous output was 0, 1, resulting in output of 0, 1. So this condition of when s is equal to 0, r is equal to 0 corresponds to the condition where the output will remain unchanged from what it was earlier. This is the memory. When you change, when you want to save something, when you store something, when you give that information and remove this stimulus, remove the excitation, still it is retained. If I give you something, if I tell you something and go away, you continue to remember it. The memory, the concept of memory, the definition of memory is that when some information is given, it is retained until it is changed further, some other way. It's erased and written over. I can change it and say, no, what I said yesterday was wrong, this is the new information. Then you will try to hold on to that new information. So the information that was put was 1, 0, and after this, we left it, removed that excitation which made it 1, 0, made it 0, 0, both inputs are 0, the output remained 1, it retained the memory. Memory retained the information 1, 0. Likewise, we put information 0, 1 and made the output 1, 0, 0, 1. After that, we removed this excitation of r is equal to 1, made it 0, output remained the same as previously 0, 1. So this is a memory state. So what did we start with? Our requirement was to store a bit, that's all, very simple requirement. I said memory is required in our sequential circuit implementation because bits are always what is required to be stored in digital systems, zeros and ones. So if I have a mechanism of storing a 1 and keeping it there as long as I want it, or if I have a mechanism of storing a 0 and keeping it there as long as I want it, I have succeeded in building a memory in a binary system, and I can replicate it any number of times to get whatever the size of the memory I want. Is that not what I said earlier? So have you now achieved that? Yes. If I want to put a 1, if I want to store a 1, the latch is the memory element. It has two inputs R and S, two outputs Q and Q bar. So if you want to put a 1 there, I want to store a 1 bit 1. Value of a bit is 1 and I want to store it. I put a 1 on S and 0 on R. It will become 1 and 0, and even if this 1 is not available to me anymore, it will continue to retain it. Until of course I change it. Of course if I change it, you can't expect it to retain what I have, what I wrote earlier, even after changing my inputs. I am not saying that. This is what I said a while ago about memory of our memory. If I give you an information, you will remember it, as long as I don't come and say, no, don't have that information, have this information, then naturally you will have to remove that information and put the new information in memory. Because we being humans will also remember, you told me that, you will immediately argue, you told me that yesterday and tomorrow, you are an unreliable person and all that. That is not what I mean here. These are electronics. They are better than us. So they don't talk back, fortunately. Right? So similarly, when you want to store a bit of 0, all you need to do is to put a 0 on this and 1 on this, and that will register a 0 in this latch, and the 0 will remain as a 0 even after removing the excitation 0 1, made it both 0 0. So this is the basic component of a memory component, which is the fundamental building block of a sequential circuit, in addition to all the combinational building block. Because combinational block is cannot be dispensed with just because we are going sequential. All circuits will still have a lot of combinational blocks, but then sequential thing is one which determines the operation, the event driven, the sequence of operations. What output now depends on what output was there earlier. All that will be done by the sequential circuit because there is memory in it. So that is the basic stuff. We have not studied, so we have studied 3 cases. We have 2 circuits. Actually, it's a combination. You call it sequential circuit, but as far as I am concerned, there are 2 NOR gates. And I have not done anything different from what we know already. Did I introduce a new concept here? No, in the sense of concept, in the sense of new theory or anything? No. There are only 2 circuits, 2 gates which you know the behavior of, and we used them in a way we wanted it. So combinational logic, the basic building block, NOR gate, which is a universal gate by the way, is used also for memory. So in every circuit, including combinational and sequential, all circuits can be formulated or designed or implemented using AND or inverter as the general case, or in a specific case of universal gates, NAND or NOR. Okay. Now, so this is a combinational circuit basically, even though there is a feedback inside it. Outside for me, there are 2 inputs and 2 outputs. I give 2 inputs, I get an output, and I have a different combination of input, I have different outputs. So I have 0 0 combination I tried, 1 1 1 0 combination I have tried, 0 1 combination I tried. I have not tried what combination? 1 1. Let me also do that. What will be the output now when S is equal to 1 and R is equal to 1? Both our inputs are 1. Output has to be 0 0, because in a NAND NOR gate, one of the outputs has to be 1. If as long as one of the inputs is 0, as long as one of the inputs is 1, the output has to be 0. So in this case, Q is equal to 0. So first of all, it defines our original idea that Q and Q bar. I put purposely Q and Q bar as one as the complement of other. that is violated here. When I say this is also 0, when I say this is 0 and this is also 0, it's not q and q bar anymore. Okay. Now, that is not a big problem though. After this I put 0, 0. What happens? Because our interest is the memory component here. Putting a data is important, but keeping it there is also equally important. That's what we said, right? Putting a bit is not the thing in a memory. I can always give you some information. If you forget it the moment I give you, or the next instant of time, what is the point in telling you something? So it is not the information that I give that is more important, it is the information storage capacity. The capacity to retain it is more important. So let us see whether it has there. So we will put 0, 0 here. What will happen now? Now both are 0. I put a 0 here. So let us assume this was a 0 and this was 0, 0, 0. The output will be 1 and 1, 0. This will be 1, 0, 0. So this will be 0 and this will be 1. Do you understand? When I say one is S is equal to 1, R is equal to 1, Q becomes 0, Q bar is equal to 0, and then after that I put S is equal to 0, R is equal to 0 as I tried in these two cases. But Q, if I analyze this way, that since this is 0, this is 0, this will produce 1, and this one will go here and make 1, 0, 0. So this will be Q is equal to bar is 1, Q is equal to 0. On the other hand, if I started with this gate, this is 0, 0, earlier output is also 0, 0, so this is 0, this is 0, this is 1, 0, 0 will result in a 1 here, that 1 goes here, is a 1, 0, this is 0. So if I started analyzing this gate first, I get 1 here and 0 here. If I started my analysis with this gate first, I get a 1 here and 0 here. So output depends on whichever gate I take first to analyze. Do you like a circuit like that? Would you like to have a circuit in which the output will depend on which gate you look at first or something like that? It's an unreliable operation. So this is Q bar is equal to 1 and Q is equal to 0. It's not for sure, no guarantee on that, because if I had taken this way, I would have gotten 0, 1. So if I can continue this, I can also write for S is equal to 0, R is equal to 0, after, of course. After S is equal to 0, R is equal to 1, I can make S is equal to 0, R is equal to 0. One possibility is the output is 1, 0. I mean Q bar is 1, Q 0. Other possibility is Q is 0. I think I have to confuse, so everything is Q bar. We'll put it as Q bar is 1, Q is 0, Q bar is 1. Here Q is 1, Q bar is 0. It is also possible. I can either get this or this. Either of the two combinations will be valid. Of course, it's not a question of my taking it, it's a question of which of the two gates acts faster. I take it this way or that way because I'm only looking at it as an observer. But the electronics inside, one of them will act faster than the other. You cannot have two gates which are identical in terms of delay. Even if it nominally, if you look at your data sheet, and to the picosecond level, picosecond accuracy, you match them, put them, there will be a small minor variation in the delay times, but these two gates, one of them will be faster than the other. So whichever gate faster, that gate gets the output of 1, the other gate gets the output of 0. So since we don't know which gate is going to be faster than the other, the output of the latch with S is equal to 0, R is equal to 0, after the condition S is equal to 1, R is equal to 1, becomes unreliable. So this and this are unreliable outputs. When something is unreliable, I will not use it as a memory at all. So I will not use this combination. So this combination of S is equal to 1, R is equal to 1, no use. I have no use for this. Since I have no use, I will not use it at all. I can say not used. Since I don't have a use for it, I will not use it. So that combination is not used at all, never used. You don't put S is equal to 1, R is equal to 1, not because it is going to blow up or anything. It's not going to blow on your face. No. Nothing is going to happen. No explosion. Don't worry. In the lab it will not happen. Put 1, 1, it will give 0, 0. Moment you remove that 1, 1, what is Q and what is Q bar is unpredictable. As your quiz marks. which will be known shortly. Right. So, we don't know what is going to be Q and what is going to be Q bar. So, because there is no point in having something which is not sure. Why do I put into my circuit something which is not sure to start with? So, I will not use that combination. So, now that means I can write the table, because I put this analysis, I write the table of the latch S R Q bar Q S is equal to 0, 0, 0, both are 0, 0. It retains, it acts as a memory. I will not be able to say, when I give S is equal to 0, R is equal to 0, I will not be able to say what is the output Q and what is the output Q bar. It will depend on what the output was before. Is it not? So that is why I call it memory in my table. Or some people write this as before state. It will not change. In some books you will see it's written as before state, or no change state, memory state. These are the different ways, synonyms they use for this. If it is a 0 and a 1, the output is a 0 and a 1. 1 and a 0, output is a 1 and a 0. 1, 1, not used. This table is not called a truth table. This is a truth table only, it is truth. It is not lie. But truth table is generally defined for combinational logic, where inputs are specified and a corresponding set of outputs are specified. Now we have dependency here. There is dependence. Here there is dependence. Like memory depends on the previous output. Such a table is called a characteristic table. But you can loosely, a lot of people call it truth table of SR, no problem. If you call it truth table of the latch, I don't have no problem. But if you want to be very correct about it, you call it a characteristic table. Characteristic, because it is a characteristic of, and I have to give a name to this latch. A latch is to hold on. The latch came from the fact that it holds on to the data, 1 or a 0. It latches onto it. So since this it uses two inputs S and R, we will call characteristic of SR latch. And why it is called SR latch, I have to tell you now. S is a condition where when you put S is equal to 1, the output remains 1, gets 1. When you put R is equal to 1, output is 0. Something becoming 1 is called a set condition in digital parlance. Digital vocabulary or parlance. 1 is called setting and 0 is called resetting. You make something 1, you say set it to 1. When you make something 0, you say reset it to 0. Set is 1, reset is 0. So we can store a 1 with an input to S is equal to 1, R is equal to 0, of course, and reset it with an input of S is equal to 0 and R is equal to 1. This is called SR flip latch, SR latch. I can also draw an AND gate, NAND gate version of this, because whatever you do with NOR gate, you can do with NAND gate. So a NAND gate version of this is, it's a reading exercise for you. This becomes yes and this becomes R. Inputs are reversed. And the characteristic table is here 0, 0 is a not permitted state. Some people also write not used instead of not used and not permitted. Permitted, of course, provided you don't care for the output. It is not permitted in the sense you will not get reliable results. So it's not used 0, 0, it's a complement operation. A 0 and a 1 will give you 1 and a 0. 1, 0 will give you a 0, 1. Right? 1, 1 will be memory. The operation is exactly complementary to the NOR operation. If you want to put a 1, you want to set the flip-flop, you need to put a 0 on S and 1 on R. Then you can set the flip-flop. Q will become 1. So because of this, and you want to reset the flip-flop, make it 0 output, you have to put a S is equal to 1 and R is equal to 0, and then remove it. When you want to retain it in the memory state, whatever you make both the inputs 1. And 0, 0 is not permitted for the same reason. After that, the next operation is unreliable. And this is a SR latch also. All sorts of nomenclature you will find in the books, because both are right. You can say SR latch with NANDs, with NAND gates. This is the simplest way of understanding this. SR latch with, this is SR latch with NOR gates. Some people, because this is condition is opposite of setting is opposite again. S is 1. Here S is 1, it sets. Flip-flop is set to 1. When S is 0, the flip-flop is reset to 0. So S corresponds to setting condition. Here, when S is equal to 0, the flip-flop is really reset. S is equal to 1, the flip-flop is reset. S is equal to 0, it's set. Because opposite, some people call this S bar R bar latch. As long as you understand the functioning of the table, functioning of this circuit. That is why if it's good enough to know that it's a NAND operation. Using NAND gates, this is NOR gate. So I call it SR latch with NAND gates, SR latch with NOR gates. But if some books may call it S bar R bar latch. Doesn't matter. If you want to use that nomenclature, it's fine with me. Because of the fact that S does not set it, S bar sets it. R doesn't reset it, R bar resets it. So we now have a basic mechanism of storing a bit of information. A bit is 1 or a 0. And entire data, whether it is a simple code converter or an L7 segment display or a huge computer with lots of data to be processed, all data are in the form of zeros and ones. So I have a basic mechanism of storing a 0 or a 1. So it's a question of replicating mass production of these latches in order to store whatever information I want. And that information is needed to be placed as the input to the additional input to the circuit. So when I want to design a circuit, digital circuit, I have a set of inputs and I have a specific set of outputs requirement. I look at the input combination and look at the specifications and try to get the outputs. Sometimes the output cannot be gotten like that. I need to know what happened earlier. So I need to have this information ready and feed it back as an additional input to the circuit. So our combinational logic theory, whatever we had seen, is not useless, it is required. It's not as if combinational logic can be forgotten from today and sequential logic is what is. Combinational logic, along with sequential logic, make digital systems tick. Real systems will have both combinational and sequential. Sequence decides the sequence of operations. Combinational logic does the actual output requirement based on the inputs. So both are required, and the basis is done. But of course, we have a few glitches to sort out. One of them is this 1001 being not permitted is something you would not like to do it, but sometimes occasionally there may be a circuit configuration which may make a 00 come to the input of this. How do you prevent it? So very difficult to, the case of the wet point, you say don't touch this wet point, you don't want to go and test it, right? When you say don't do it, you do it. Have you seen that? No, whenever somebody says wet pine, you want to see how wet it is. And sometimes it gets stick to your eye and then keep rubbing it. So when you say something is not permitted, you would like to try to do it and see what happens. Of course, not purposely. Sometimes the circuit behavior, the previous stage which feeds on to this stage, may create a glitch of 11 or a 00, and you don't know, something may happen. So the circuit, see, something may happen, don't be too nervous about it. It is only a condition of unreliability which I don't want. We want certainty, we don't want unreliability, uncertainty. So we have to remove that. We'll have to see how to do that. And do you really, if you want to store a 1 or a 0, do you really want to store a 1 and put a 1 and s and r is equal to 0? And to store a 0, I have to put a 0 and r is equal to 1. Why should I give 2 inputs to store 1 output? So I have to remove that. So I need to work a lot more on this. How am I going to remove 1 1 or 0 0 case, which is not permitted case? How am I going to have 1 input? If I want to store 1, I should be able to give 1 and store it. If I want to store a 0, I should be able to give 0 and store it. Don't ask me if you want to store a 1 and give a 1 and a 0 and then I will store 1. If you want to store 0, give a 0 and a 1 and then I will store 0. That's not good. So we'll have to look at some of those extra things that we need to go with that. This is only very, very raw, basic, the fundamental building block, like a gate, 2 input gate we started with. So the similar hierarchy here, the sequential is the simplest or latch. We'll modify it to make it more useful circuit, and then we'll look at some of the applications of these circuits.